Springs engineered for automotive, agricultural, and industrial applications are crafted at Bet Spring Manufacturing. Cold wound coil springs start with pre-measured high-tensile chrome silicon wire. The material passes through rollers and fulcrum pins before coiling tightly around a precision-ground arbor. This method produces lighter springs with smaller diameters, allowing increased travel and deflection. Engineers design each spring according to specific load and performance requirements. For larger applications, hot wound coil springs are used. Bars are heated in a low-emission walking beam furnace to 1,750 degrees Fahrenheit, then coiled around fixed mandrels. The quenching oil step locks in strength, while tempering ensures durability. Leaf springs follow a similar approach, tailored for heavy-duty use. After forming, all springs undergo rigorous measurement, testing, and quality checks to meet ISO 9001 and industry standards. The integration of automated systems with material expertise enables efficient production and consistent results. BETS combines design, prototyping, and testing to deliver springs that balance performance, weight, and durability. Every step emphasizes precision engineering and strict adherence to customer specifications. NNN.
Forging iron is both craft and endurance, where pressure and heat define strength. In northern Spain, Irizar Forge continues a 90-year legacy shaping massive hooks for lifting and marine industries. Their expansion into oil and gas brought higher technical standards, requiring audits, ISO qualifications, and direct collaboration with EPC contractors. Every forged piece carries certification, trust, and family heritage, proof that skill and persistence can shape not only steel, but entire generations of excellence. And then,
the Turbine Series 8000 redefines large-format bending with unmatched strength and versatility. Operators can plan complex bends efficiently through the intuitive multi-touch display. NTHE-CNC controlled lower tool shifts seamlessly, adjusting to each component's dimensions. Large nesting heights up to 880 mm accommodate sizable sheets with ease. Watching the tool and operator move in harmony highlights the sophistication behind modern bending technology. NHIGH pressing force, up to 6,000 kilonewtons per meter, delivers precise, clean bends every time. The ACB measurement system ensures perfect angles, minimizing errors and material waste. Energy-efficient drives reduce consumption while maintaining output. Ergonomic supports and folding aids enhance operator comfort without slowing production. This machine exemplifies how industrial innovation boosts both performance and usability.
The workshop hums with industrial intensity as the Uniforce 7 takes position. First, the C45 material is prepared, and the large 250 mm face mill engages, removing excess layers with steady precision. The way the machine adjusts feed and depth is truly impressive. Next, a 250 mm disc cutter slices through with calculated pressure, shaping components efficiently. Engineers watching this will appreciate the balance between speed and control. Finally, a smaller 160 mm face mill finishes the surfaces, creating smooth, uniform planes. This level of consistency is exactly what high-demand parts require. Each operation showcases the machine's adaptability and strength. Noun.
Shenyang Gatai Hydropower transforms raw metal into high-performance Pelton turbine runners with systematic expertise. Sheets and castings undergo precise CNC machining, shaping blades and hubs with exacting measurements. Specialized heat treatment enhances durability, while welding secures structural integrity. Advanced simulation and endoscopic inspections validate each component before assembly. Operators coordinate steps to maintain consistency across the turbine parts. Every adjustment and alignment ensures peak efficiency and longevity. This workflow highlights the fusion of engineering skill and methodical process in producing world-class hydropower equipment. Enter the workshop where Gute Kunstfedern shapes wire into precision springs. Automatic winding machines craft compression and extension springs to exact dimensions. Bending and forming stations adjust angles and loops, while integrated grinding machines refine surfaces for consistency. Optical inspection systems verify every coil and end shape, rejecting any deviations. Operators coordinate these automated processes to sustain high output without compromising quality. Each spring passes through systematic alignment and verification, ensuring reliable performance in demanding applications. The workflow exemplifies how methodical machinery and human oversight combine to produce durable, precise springs.
Hydropower storage at Limern relies on steel pipelines engineered to withstand immense water pressure. Steel plates, 6 centimeters thick, are preheated and rolled into precise curves over 4 to 6 hours. The dimensions of each segment are controlled down to the millimeter, guided by computer systems, ensuring exact conformity. Edges are prepared thoroughly for welding. Every adjustment impacts how the pipes will endure the forces in the shafts. Ends of the massive plates are aligned, preheated to optimal temperature, and tack welded. A welding robot then completes the final seams in multiple layers over 16 hours. Continuous monitoring of current and temperature guarantees structural integrity. After welding, seams are ground smooth and 4 injection holes are drilled for concrete infill during installation. Producing 6 to 7 pipes weekly highlights the scale and precision of the operation. Pipes weighing up to 20 tons are transported individually via cableway over 1,000 meters of elevation to storage near the Mutsee. They then travel 3 kilometers through a tunnel before final placement in the shafts. In the shafts, multiple pipes are welded together by top welders under 40 degrees inclines, with repeated magnetic inspections using fluorescent fluids to detect flaws. Every stage showcases a balance of engineering, logistics, and human skill. Final corrosion protection is applied before installation. The steel infrastructure ensures the pumped storage plant functions reliably, turning the natural height difference between Limern and Mutsee into a dependable energy reserve. And an The LCT 613 cut-to-length line transforms metal coils into precisely measured sheets with impressive efficiency. Each coil starts its journey on the uncoiler, where careful handling prevents deformation. After being released, the metal passes through a straightening machine that removes any curvature, ensuring the material is perfectly aligned. Precision rollers further refine the sheet, maintaining exact dimensions and smooth surfaces. Once straight and uniform, the material enters the cutting unit, where it is cut to predetermined lengths. This step combines speed and accuracy, highlighting the line's engineering excellence. Cut sheets are then transferred to a conveyor system, which aligns them automatically for consistent stacking. Operators supervise the process, adjusting settings and monitoring performance to maintain throughput and safety. The final stage uses an automatic stacking system that bundles the sheets neatly, reducing manual handling and increasing efficiency. Synchronization between all units ensures smooth operation, minimal downtime, and consistent output. The line is designed not only to optimize productivity, but also to protect operators by controlling pinch points and maintaining safe distances. Every movement of the LCT 613 reflects careful integration of mechanics, automation, and control systems. From coil loading to bundled sheets, the line delivers a seamless process that balances speed, precision, and reliability, making it a critical asset in modern metal processing facilities. Precision engineering turns raw steel panels into a fully structured BMW 3 Series F30 body, where every weld and alignment matters. The assembly hall orchestrates a sequence of automated and human-guided operations to craft a vehicle's foundational structure. End steel panels are first positioned on the body frame, secured for exact alignment. Robotic laser systems weld the front bulkhead with wire-guided laser technology, ensuring each joint withstands structural demands. The accuracy of these robots allows minimal material stress while maximizing structural integrity. Advanced sensor arrays continuously check for even the smallest deviations in positioning. Next, the floor assembly undergoes robotic welding, combining multiple components into a strong base. Spot welds reinforce key connection points. Engineers can adjust the robots for subtle tolerances, reflecting BMW's commitment to adaptable production quality. The car's skeleton then receives additional reinforcement through robotic welding of the body frame ribs, connecting pillars, and side supports. Material flow analysis ensures that each panel maintains optimal strength under stress, and adhesives are applied on the side frames and roof, with robots controlling quantity and placement precisely. The side frames are automatically fitted onto the floor assembly, followed by careful placement of the roof. This coordination of welding and adhesive ensures rigidity and long-term durability under dynamic driving conditions. Thermal expansion of panels is factored in to avoid stress over time. Once the main shell is complete, external panels including the fenders and hood are attached with exact alignment. Each component is positioned using automated systems, reducing human error. The interplay between robots and quality monitoring provides consistent results that meet BMW's global standards. Throughout this process, operators monitor all parameters to ensure safety and compliance. Spot welds, laser joints, and adhesive bonds undergo verification to maintain strength and longevity. Continuous feedback from sensors allows the production line to adapt in real time to minor variations. And finally, the finished body shell proceeds to the next stage of painting and final assembly, fully prepared to receive mechanical and electronic components. Every weld, every adhesion, is a calculated step toward a vehicle designed to perform reliably for years. BMW F30 body production combines robotic precision, innovative joining methods, and careful oversight, ensuring each car meets stringent structural, safety, and quality standards.
Guided by REPKON's precision mechanisms, steel sheets start their journey toward becoming strong, uniform LPG cylinders. Each sheet is rolled and stretched to form the seamless body of the cylinder. Operators ensure that the initial alignment is exact, providing a uniform wall thickness and a flawless cylindrical shape. Next, the valve bosses are machined and welded onto the cylinder body. This stage demands coordination between the welding system and precision fixtures to maintain proper orientation. Each valve boss undergoes verification to confirm proper seating and alignment, critical for safety and functionality. NTHE foot rings are produced and attached, stabilizing the cylinder for handling and use. This step involves accurate positioning and robust joining methods to ensure structural integrity. And once assembly is complete, cylinders move through a heat treatment furnace. Controlled heating strengthens the steel, improving durability under pressure. After cooling, each cylinder is hydrostatically tested using a carousel system. This test applies internal pressure well above operating limits to verify strength and detect potential leaks. And following testing, cylinders are cleaned with shot blasting, removing surface residues and preparing them for coating. The wet painting line applies protective layers uniformly, enhancing corrosion resistance and extending service life. And finally, the finishing line inspects, marks, and packages each cylinder. Operators confirm that dimensions, coatings, and fittings meet strict standards. The workflow highlights a blend of automation and skilled supervision, ensuring that every cylinder leaving the line meets stringent safety and quality requirements. Seeing these steps in action reinforces how industrial precision and systematic procedures secure reliability in high-pressure equipment. Feel the force of precision as the smart 13 BAR automatic stirrup bender shapes steel bars up to 13 mm in diameter with exacting control. The barcode reader loads processing programs, guiding each bend to meet strict specifications. Pre-arranged positions adjust for different bar sizes while digital electric servo motors deliver consistent, accurate bending. Waste is minimized as the machine optimizes bar usage, and single-direction operation efficiently produces stirrups and cut-to-size bars, even for double 10 mm bars. Mobility ensures it can be positioned directly on any job site, supporting flexible assembly. Watching operator and machine work together highlights the streamlined workflow achieved through automation. Productivity and precision are on full display. .NE The Divamek LCL Chopafina is designed to handle thin metal sheets with remarkable care and efficiency. Sheets are initially cut lengthwise, creating manageable strips that prepare the material for orderly handling. Cutting these sheets in precise lengths ensures that each strip can be twisted and stored without unnecessary stress or deformation. This initial step highlights how attention to basic preparation can prevent complications later. And after cutting, each strip is twisted into a coil. Twisting reduces the sheet's exposed surface area, making storage more compact. Operators monitor coil uniformity to maintain even tension throughout each twist. The twisting process also minimizes surface scratches, preserving the sheet's quality. Tracking each coil's orientation helps avoid misplacement or misalignment in subsequent handling. Once coiled, the metal strips are aligned systematically. Proper alignment ensures stability during movement and prevents deformation of delicate sheets. Even small improvements in arrangement can save time and enhance safety in industrial operations. Attention to the position of each coil reflects the value of precision in seemingly routine tasks. Organizing coils by batch or production date facilitates efficient inventory management. Operators often coordinate their steps carefully to maintain consistency and protect material quality. Marking each coil clearly can prevent errors and streamline workflow. This sequence shows that practical methods and thoughtful handling are the backbone of reliable production. Maintaining uniformity across coils also allows smoother workflow for downstream processes.
This video captures the journey of raw bauxite transforming into high-grade aluminium at the Kitimat aluminium smelter. The modern facility combines cutting-edge AP40 technology with decades of metallurgical expertise to deliver consistent, quality production. Bauxite, the main ore, is first crushed and refined into alumina. 4 tons of bauxite yield 2 tons of alumina, which is the core material for smelting. This ratio underscores the intensive process required to convert abundant ore into a usable metal. The refined alumina is fed into electrolytic reduction cells or pots, where a mixture of anodes, pitch, petroleum coke, and controlled electric current separates molten aluminium from oxygen. Anodes are manufactured on-site, baked at up to 200 degrees Celsius, and fitted with aluminum stems in the rotting shop before placement into the pots. Each anode assembly functions for roughly 20 days, and replacements occur without halting the smelting process. The precision in handling and timing ensures a continuous output of high-quality metal. With 384 pots distributed across 4 buildings, electrical current runs uninterrupted, driving the chemical reduction while sustaining operational reliability. Molten aluminium is siphoned from the pots into crucibles, and 8 crucibles are used to fill a holding furnace. The furnace tilts to allow metal to flow into molds for casting, producing ingots, she ingots, and sows according to customer specifications. Automation and temperature monitoring along the casting line guarantee consistent material quality. NTHE finished aluminium is then shipped via Kitimat's ice-free deep-sea port to customers in Asia and North America. Advanced environmental controls, including gas and fume treatment systems, reduce emissions by 50%, demonstrating a commitment to sustainable production. The smelter represents a balance of scale, innovation, and environmental stewardship, making it a benchmark in modern aluminium manufacturing. And over decades, Rio Tinto's continuous modernization and skilled workforce ensure that the Kitimat smelter remains a world-class facility, producing aluminium reliably for the global market. N. Cables designed for low and medium voltage energy systems are being produced. The combination of natural and colored PVC guarantees consistent insulation quality. Extrusion shapes the PVC into precise layers. 8 mm electrolytic copper film is applied to create reliable conductive paths. Proper layering directly impacts performance and safety. XLPE and HFFR coatings are added for durability and fire resistance. The cables undergo rigorous measurement and lab testing to meet TSE, VDE, IEC, and GHOST-R standards. This production line reflects efficiency and strict quality control. NNNN.
Cables take shape with precision as they pass through the UVM Versailles machine, a machine built for consistent twisting and assembly. Operators first feed individual conductors into the machine, ensuring alignment for consistent tension throughout the twisting process. The machine's guide rollers direct each wire, maintaining proper spacing and preventing overlaps that could compromise insulation or performance. NA's twisting progresses, speed and torque are adjusted according to cable specifications, allowing uniform lay length across the entire assembly. It's fascinating how mechanical coordination and monitoring ensure flawless results. After twisting, the cables pass through compacting rollers, which consolidate the strands to improve density and mechanical stability. And quality verification follows immediately, with measurement systems checking lay length, diameter, and overall consistency. Any deviation triggers adjustment mechanisms that fine-tune tension and alignment. Completed cables are then guided onto spools for storage or transport, preserving their structural integrity and readiness for downstream applications. Metal beams arrive at J&D Pierce's Glasgow facility, each inspected for quality and measured precisely. Cutting stations shape the steel to required dimensions, ensuring minimal waste and accurate fit for structural assemblies. Drilling and punching operations follow, preparing the beams for connections. Workers align components on large assembly tables, using temporary supports to maintain geometry. Welding stations secure joints, and experienced operators monitor each seam for integrity. Plates and reinforcements are added where necessary, strengthening key points. Once completed, the structures are lifted and transferred to inspection zones. Final checks verify dimensions and weld quality, ensuring safety and compliance before delivery. Seeing steel transformed with such efficiency is impressive. Precision is crucial when dealing with massive rotating components like a girth gear. At the facility, the girth gear is first transported to the assembly area and carefully positioned on specialized alignment fixtures. These fixtures support the gear while allowing controlled adjustments along multiple axes. Technicians begin by measuring axial runout, confirming that the rotation stays true to the intended centerline. Each measurement guides incremental shifts in the gear's position. Radial runout is then checked, ensuring the outer surface remains consistent throughout rotation. Alignment fixtures are designed to facilitate these fine adjustments efficiently, reducing the risk of misalignment that could compromise machinery performance. It's impressive to witness the combination of mechanical leverage and engineering judgment at work. Bolts and clamps are applied to secure the gear once acceptable runout readings are achieved. And during the reversal operation, operators rotate the girth gear carefully while maintaining control over every adjustment. Specialized tools and measuring devices track each change, allowing corrections in real time. Every small calibration step contributes to the long-term reliability of the equipment. As the process continues, attention to both axial and radial tolerances ensures the gear's performance will meet design specifications. Once alignment is completed, the gear is verified again to confirm that all readings remain within limits. Technicians document measurements, creating a record that guarantees consistency and traceability. Seeing such a complex component reach its final aligned state is genuinely satisfying. The structured approach, combining precise fixtures and experienced oversight, highlights how advanced industrial processes maintain quality in heavy-duty machinery. Final adjustments are minimal but essential for optimal operation. This workflow exemplifies the critical balance between engineering discipline and practical execution, making high-stakes alignment tasks manageable and reliable.